Alright, hello everyone. Welcome back to the F equals MA Club. This is going to be day 4, where we're going to be talking about conservation of momentum. Today's going to be a much shorter lesson than usual since I kind of just made this on the fly. Alright, so just a little bit of review. Remember that momentum, its equation is going to be P equals mv, where P equals momentum equals mass times velocity. Remember that impulse is going to be your change in momentum. So impulse, which is J, is going to be equal to your F dt, which is equal to your change in momentum delta P, which is equal to your M dv because your mass won't change. So just a little tip, remember that means that the area under a forced time graph would be the momentum. All right. So the big thing is just conservation of linear momentum for now. So we have our initial momentums equal our final momentums, and sometimes maybe plus some non-conservative force. So m1v1i plus m2v2i is going to be equal to m1v1f plus m2v2f. And ignore what I just said before. Remember that collisions, these are going to be one of the most tested parts of the F equals ma competition. There's going to be two types of collisions, elastic and inelastic. And remember, partially elastic, partially inelastic, those are going to be values in between those. So these are some good equations, especially these two, to have memorized. And just remember this one whenever you're trying to find elastic or trying to find the amount of energy lost from inelastic. All right, so let's just move straight into our questions. So let's look at our first one. So a 12 kilogram block moving east at 4 meters per second collides head on with a 6 kilogram block that is moving west at 2 meters per second. They stick together after the collision. What is the loss of kinetic energy in this collision? All right, so this is an inelastic collision, and it's just trying to ask us to find the amount of energy lost. All right, so let's begin. So we have a 12 kilogram block, right? We have a 12 kilogram block moving in this direction at, what is this, 4 meters per second? And we have another block, what is that one? That's going to be 6 kilograms, right? 6 kilograms moving in this direction at 2 meters per second, right? There's no friction, and they stick together after they collide, right? Okay, so let's use our inelastic equation, right? So our initial velocity, right? Not our initial velocity, our initial momentums, right? For inelastic, remember that they stick together, so it's going to be Vf. That's not supposed to be that. That's supposed to be an I. Vf times m1 plus m2, right? Okay. So first one is, what is that? 48. 48 plus 2 times 6 is 12 equals our Vf times 12 plus 6, which is 18, right? Oh, sorry. Since this is moving, this velocity is technically moving negative relative to this. This is going to be 48 minus 12. So let's erase this, right? And that's going to be 48 minus 12. So that means that we have 36 equals 18 times our final velocity, right? So our final velocity is going to be equal to 2 meters per second, right? Okay. Now that we have that out of the way, let's just move this. No, please don't rotate. No, now. Okay. Let's move this over here and make this. Okay. This is not cooperating with me. Alright, so. Ooh. Now it just looks stretched. Okay, so now that we have our final velocity is equal to 2 meters per second, right? So we can use our conservation of energy equation back there, which is 1 over 2 m1 v1 initial squared plus 1 over 2 m2 v2i squared. Sorry, this is getting a little bit funky today. It's going to be equal to 1 over 2, and since both of these have the same velocity, we could just take the velocity out, right? Times m1 plus m2, right? So let's start putting these in, right? So we have 12, 12, 4, 16, right? 16, 8. So this is 4 squared. 4 squared is 16 times 12 times 1 over 2. We can cross these, and this will be 8 plus 1 over 2 times 6, right? Times 2 squared. This is going to give us 4, right? We can cross these out. This is 3 times 4, right? This is going to be equal to 1 over 2 times 2 squared. So that's 4, right? We can cross these. That's 2. 2 times 12 plus 6 is 18, right? So now we have 96, right? Plus, what is that? 12, right? Is going to be equal to 36 plus some lost, some energy loss, right? So KE lost, right? So we have 96 plus 12 minus 36, basically, right? So this is going to be essentially 96 minus 24, which is going to give us 72, right? And if we look back on our slide, not our slideshow, our worksheet, that's going to give us D, right? Okay. So our next problem is going to be a particle at rest explodes into 3 particles. And this one, like, it takes a little bit more time to understand, but once you got it, you got it. Ooh. So a particle at rest explodes into 3 particles, right? Equal mass, absent of external forces. And the part that says at rest and absent of external forces, these parts are going to be very important, right? So 2 particles emerge at a right angle to each other at an equal speed v. What is the speed of the 3rd particle, right? All right. Let's do this. So we have 1 particle that explodes into 3 parts, right? So, and 2 of those parts have a right angle to each other at a speed of v, right? So each of these have a speed of v, right? Remember that there is conservation of linear momentum, right? So since our starting momentum is going to be equal to 0, that means that, okay, let's just put like an I here for initial. That means that our final momentum is going to have to equal our initial momentum, since there's no external forces, which is going to equal to 0, right? So we already have 2 forces moving in these 2 directions, so we can do a little bit of like vector addition, right? So we have this, the resultant vector is going to look something like this, right? Which means that the 3rd particle is going to have to move directly opposite to that 3rd resultant vector, right? With a separate speed. So if we add these together, this is a 1, 1, right? This is VV, VV, right? So we could say that this is basically like a right triangle, a 45, 45, 90 triangle. We have 1 to 1, right? And we know that this is 90 degrees. And so our resultant is going to be square root of 2, right? And since these are all multiplied by v, these are all multiplied by v, right? So that's multiplied by v, that's multiplied by v, sorry. That means that our resulting, our 3rd particle, the magnitude of its velocity is going to be square root of 2 times v, right? And if we look back at our slideshow, that's going to give us b. All right, on to the 3rd problem. This is going to take a little bit more time, but once you've got it, again, once you've got it, you got it. And this really isn't too hard of a problem. It just takes some time. So we have a 5 kilogram block, right? We have a 5 kilogram block with a speed of 8 meters per second. It travels 2 meters before colliding with another block, right? Perfectly elastic to a 15 kilogram block, which is at rest initially. And there is a coefficient of kinetic friction between the blocks and the road. And that coefficient is going to be mu equals 0.35, right? And it's asking us how far the 15 kilogram block travels before coming to rest, right? All right, I suddenly realized that I forgot my calculator, so I'm going to be doing these by memory. So we have a 5 kilogram block that's moving at 8 meters per second, right? This is 2 meters, right? So let's figure out how much the 5 kilogram block loses, like how much speed it loses, right? So we have our force, right? The only force acting on this block right now, since this is its constant velocity, right? So the only force acting on it is friction, right? And our friction is going to be mu n. Mu is 0.35. Our n is going to be equal to mg, which is going to be 50. So we have 50, right? That's our times 0.35. Sorry, 0.35 over, what is this? The mass, right? So because we have what this is doing, this is total forces over mass equals acceleration, right? F equals ma. And so our total force, the only force that's acting on it, is going to be your friction force, right? So the basis of this, we don't even need to write that much. This is just mu mg over m, right? And so these cross out. That gives your acceleration as mu g. So that's going to give you 3.5, right? A equals 3.5 meters per second squared, right? So we can plug this into our handy dandy kinematic equation, which is vf squared equals our initial v squared plus 2ad. Right? And we have our distance, we have our acceleration, we have our initial. So we have 64 minus, since this is negative 3.5 meters per second, since this is moving in the other direction, so that's going to be 2 times 2 times 3.5, which is going to give us 14. And that's going to give us our vf squared, so we can just square root that. That gives us our final velocity of a square root of 50, right? All right. So let's shrink this just a little bit, right? And then we can move this over. So we now have that at the point of collision, right? Our VF is going to be equal to the square root of 50 meters per second. So let's plug this into, this is a completely elastic equation, right? So remember our formulas, which is that our second velocity, final, is going to be equal to m2, 2m1 over m1 plus m2 times your v1, right? So this is going to be equal to 2m1. Your first mass is 5, right? So this is going to be 10 over m1 plus m2. That's 5 plus 15, which is 20 v1. v1, which is square root of 50, right? So that's going to be your v2 prime. And that's going to give you 1 over 2 square roots of 50, right? All right. So now we have the velocity of this second block after collision, right? And we don't need to worry about the first one since that is basically irrelevant to the question. So let's plug that back into our kinematic equation, right? So Vf squared equals V initial squared plus 2AD. Remember that our acceleration will always be mu g, right? Because m always cancels. So our acceleration is still going to be negative 3.5 meters per second squared. So we have our acceleration. We have our initial velocity, right? That's over here. We don't have a final velocity, right? So that means that we're trying to find our distance. So our distance is going to be equal to, so we can just first write this out. So V naught squared is equal to essentially 2 times 3.5, right? Because this flips, times d. We have our v naught squared. That's going to be that squared, which is going to be 50 times 1 over 4. So that's 12.5 over, since we have to divide 7 on both sides to get rid of this, right? Divided by 7, that's equal to d. So d is going to give you around 1.79 meters. And if we look back on our worksheet, that is going to give us answer B, right? All right. So here's where the impulse stuff comes in, right? There's actually a much harder impulse question on one of the FMUC things, but I just didn't bother putting it in. A 5 kilogram object undergoes a time-varying force shown in the graph below. If the velocity at t equals 0 seconds is 1 meter per second positive, then what is the velocity of the object at 7 seconds, right? T equals 7 seconds. So let's first draw out this graph. Just gonna get a haphazard drawing of this, right? So we have some force there, then we have something that's more like that, 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 sure. And then we have a little bit here. So how this graph goes is this has, so this is 1, 2, 3, nope, 1, 2, so 1, 2, 3. That's what we're assuming, right? And that goes with that. So this is 1, 2, 3, 4, 5, 6, 7, right? Okay, so this is our force in newtons. This is our time in seconds, right? All right, so remember that the area under a FT, a force time graph, this is going to be our momentum, right? Okay, so we're trying to find from 0 to 7 seconds, right? So we have, basically we need to find the antiderivative of this. And then, so the antiderivative of this, right? So the antiderivative of what is essentially our impulse, I'm assuming it's dt, is going to be equal to our change in, is going to be equal to our momentum, right? Which is going to be equal to our mv. So what we can do is we can find the area of this. Well, okay, so this is going to be p plus c because we have a constant, right? Which is equal to mv plus c. So what we can do right now is we find the antiderivative, so the area under the graph, right? From 0 to 7. And so that's going to give us, let's first look at this, right? So we have something like this, right? So we first have a triangle here. This is 1, 2, 3, right? So this is 3 times 3 divided by 2. So this is 9 over 2. Is that correct? 1, 2, 3, 1, 2, 3. That looks right. I'll correct it later if I'm wrong. We also have here, right? This is 4, right? This is 4, this is 2. So 4 times 2 divided by 2, that's going to give you 4. And this bottom part, this is going to be just 4 times 1, which is going to give you 4, right? Oh, please work. So that means that our total area is going to be, what is this? So that's 4 plus 4 plus 4 plus 1 over 2, right? So that's going to give us 12.5, right? That's going to be our momentum. I forgot the units, which equals to our mass. Oh, kilogram meters per second. It doesn't matter. So that's going to equal to our momentum times our velocity plus a constant, right? So we can divide by our mass on both sides, right? And we're given our mass, which is 5. So this is going to be 12.5 over 5 is going to be equal to our v, plus, remember that t at 0 seconds is going to be 1 meter per second, right? So our final velocity is going to be equal to 12.5, oh, 12, sorry, critispasming today, 12.5 over 5 plus 1, which is going to give us, what is that, 2.5 plus 1, which is going to be 3.5 meters per second at t equals 7 seconds, right? And if we look back at our slideshow, we can see that that's going to give us option C, right? Okay, that's the question. That's the answer. So let's move on. So we have information of associated with these two questions, right? So we have cards A, B, and C. Masses are M, 3M, and 9M, right? Originally at rest at 1 meter, and that's at 2 meter. That really doesn't matter because the entire thing is frictionless, so it can be however long it wants. It's just that when it collides, velocity. So, assuming that all collisions are completely inelastic, what is the final speed of card C, right? So let's first draw this out. So we have a lot of cards, right? We have one here, we have one here, we have one here, we have one here, right? And we don't even need to mind where they are, and we can draw wheels. It doesn't matter. So we have A, B, and C. So this is M, this is 3M, this is 9M, and this is our initial velocity, right? So assuming that these are all inelastic, which means that they stick together, what is our final velocity, right? So let's think about the first card. So remember that M, so I'm just going to substitute these. And so it's supposed to be M1, V1, da da da. So this is going to be M, V naught is going to be equal to our final velocity, right? Final velocity m plus 3m, right? Which means that this is going to be v naught is equal to vf, and this is going to have an m times 4m, right? So these can cross out. That means that v naught is going to be 4 times our final velocity of this, which means that our final velocity is going to be 1 over 4 of v naught, right? And so now we go on to the next one, right? So we have our, what's our mass? So 4m times 1 over 4 v naught, which basically is just v naught, right? mv naught is going to be equal to our final velocity plus m plus 3m plus 9m, which is going to give us 13m, right? These m's once again cross out, which means that our final velocity of all three carts, when the inelastic collision occurs on cart C, that means that our final velocity is going to be 13 times our final velocity gives us our initial velocity, which means that our final velocity is going to be 1 over 13 times our initial velocity. And technically, you could have just plugged it in from here, where it's mv initial is going to be equal to our final velocity times m plus 3m plus 9m here as well. And so that would give you 13m v final is equal to m v initial. These m's cancel, and we can just go to here, right? All right. So next part, right? It's asking, So next part asks, assuming that all collisions are completely elastic, what is the final speed? So remember that we're just measuring these ones, right? The ones that are being collected into. So our second, velocity, right, is going to be equal to our, 2m1 over m1 plus m2 over v1, right? And in this case, this is v naught. This is just going to be m. Okay, let's just plug this in, right? So we have v2 prime, which is, it's going to be equal to 2m over m plus 3m, right? So that's going to give you 4m times the initial velocity. So these can cross out, and we can determine that this is going to be 1 over 2 times the initial velocity, right? Now we move on to the next one, right? So now we have, now 2 times m1, which is, in this case, it's going to be this one, which is going to be 2 times 3m over m1 plus m2. So 3m plus 9. So 3m plus 9m times what is essentially, remember that now that our velocity here is going to be 1 over 2 our initial velocity, right? So times 1 over 2 v naught. So that's going to give us, so this is 6, right? This is going to be 12m. We can cross out the m's again. This gives us 1 over 2. So our final velocity of our cart C is going to be 1 over 2 times 1 over 2 v naught, which is going to give us 1 over 4 v naught. There we go. And so if we look back, that's going to give us option B. All right, time for the final question. This is going to be a little bit more tricky, but it's quite an interesting problem. So what does it say? Okay, yeah. So an object of mass 1 initially moving at a speed of v naught collides with an object of mass So basically it's colliding with a mass that is a given constant smaller, right? Less heavy, where that's smaller and it's initially at rest. So it can be completely elastic, completely inelastic, or partially inelastic. So after the collision, they move at speeds v1 and v2, where v1 is going to be the speed of your first mass and v2 is going to be the speed of your second. So assuming that it's one-dimensional, the object cannot pass through object 2. After the collision, the speed ratio v1 over v0 of object 1 is bounded by one of these 5 options, right? This is quite an interesting one, and it utilizes basically all the formulas that are provided. So now, instead of focusing on v2, we're going to be focusing on v1. So we have 2 cases, right? We have one where our object is going to be elastic, or our collision is going to be completely elastic, and we have one that's completely inelastic. And the reason why we aren't doing anything that's partially inelastic is because partially inelastic, right? So partially inelastic is going to just be somewhere on this spectrum, where this side is completely elastic, this side is completely inelastic. This partially inelastic is going to be somewhere on this spectrum, right? We can say something like that, right? Okay, so the main ones that we need to find are completely elastic and completely inelastic, right? So let's first do elastic. So we have our formula, which is V1 prime is going to be equal to M1 minus M2 over M1 plus M2 times V1. It's going to be equal to our change, right? So we have M2. Remember that M2, this is going to be a big thing, so I'm going to use red. M2 is equal to alpha M1, where alpha is less than 1, right? So we can say that this is equal to M1 minus alpha M1, right? Over M2, M2, over M1 plus alpha M1. This is multiplied by V1, right? Which in this case we can say, what is it in the equation? It's going to be V0, right? We can say that's V0, right? And we don't even need the prime here because it's denoted as V1. So that means that this is going to be M1 times 1 minus alpha, 1 plus alpha, and this is all multiplied by V0, which means that our ratio for elastic is going to be this, right? Or V1 over V0 is going to give us this. So let's look at inelastic, right? So that means that our, let's just write this out. So M1 V0, right, is equal to our our VF, right? So that's going to be our V1 times M1 plus M2, right? So we're trying to find this, right? So V1 is going to be equal to M1 over M1 plus M2 times V0, right? And we can once again do this little thing where this is going to be equal to M1 over M1 plus alpha M1 V0, which is going to be equal to M1 times 1 over 1 plus alpha times V0, right? And since we're trying to find the ratio, that means that our R1 is going to be equal to this, right? So that means that the bounds of this are going to be, let me see, what does it say? So R1, oh, and the thing, yeah, okay, so, yeah, so our final speed ratio, right? Since both of these have M1, we can technically eliminate these, right? Because we're comparing those. So R1 is going to be bounded by 1 minus alpha over 1 plus alpha, right? These are all together. And we have 1 over 1 plus alpha, right? Right? Because if you think about it, that's how it's going to work. And so if we look back on our little worksheet, we're going to see that that's going to give us answer B. Yeah. And there's a variant to this, I can pose it as a challenge, where it's trying to find the speed ratio of, I think, V2 and V0. So, yeah, that's about it. Thank you so much for watching. I hope you have a good day. We'll see you next week.